Okay, hello everyone. For this, the last talk of the session, I believe, we have Gushu Lee. He'll be talking about projection-based runtime assertions for testing and debugging quantum programs.
Okay, thank you for the introduction. And I'm Gushu, a first-year PhD student from University of California, Santa Barbara. Today, I'm going to talk about our recent work on designing assertions to help with quantum program testing and debugging. This is a joint work with Lee from MPI, Nengkun and Mingsheng from University of Technology, Sydney, and Yufei and Yuan from UCSB. Quantum programs are error-prone. It's already quite common for programs to make mistakes in classical programming, and things are even worse in quantum scenario, because quantum programs run in a quantum manner, and we humans live in a classical world. For example, here I took a screenshot from one of the IBM's GitHub repo. It was reported that, okay, the example quantum teleportation program is run. Actually, the orders of two single qubit gates are interchanged here. Quantum teleportation is already one of the simplest quantum programs and is usually considered as a quantum hello world here. There are just 3 qubits and 6 gates, and mistakes can be made even in such simple scenarios. So we hope to improve the reliability of quantum software. And in this study in particular, we are targeting a scenario that, okay, once we have a quantum computer, how can we test the quantum programs we run on it? And to be clear, first I must emphasize that testing is different from verification. Verification may be able to guarantee the overall correctness, but it is usually very expensive because it will consider all possible executions with all possible inputs. Software testing is another approach. It can, for example, you write some program and you can run it with some specified input, and you can see if the program gives you the output you expected. It is a little bit weaker, but still quite useful. Another keyword we will talk about is assertion. The term assertion in the scenarios of software testing is a predicate on some program variables at a place in a program. When running an assertion, the program will check if the predict in the assertion is satisfied. If so, the program will continue. If not, the program should abort and report the error. In a quantum scenario, an assertion, for example, in a quantum circuit can be considered as a circuit block on some qubits. And in this study, we'll figure out how to design and implement these blocks. In the rest of this talk, I will start from the theory side of the assertion design and then discuss some practical implementation issues. Testing a quantum program state on a quantum computer is somehow like just the physicists doing quantum experiments in their labs. So first, can we learn something from existing quantum information science? Actually, in existing quantum information processing, one typical approach is to do quantum state tomography. Yes, quantum state tomography can fully characterize any state role, but it's generally too expensive because we need to repeat the state propagation and the measurement many times. And this approach is not scalable. Can we do something simpler and easier, like in some computer science style? Assertion testing actually has been invented for quantum programs, and assertions can be much simpler when the state can be expressed in a classical language. For example, when the predicate says, okay, the state is in a classical bit string, you can just measure each qubit and see if the output matches. But in this case, the expressive power is very limited. And the existing assertions describe quantum state properties using classical languages, and they can only express 3 types of states listed here. And many complex intermediate states cannot be asserted. Another implicit efficiency here is that, okay, measurement in the assertion checking may destroy the tested state and make the follow-up execution meaningless. So in this study, we hope to have a new approach with 2 objectives. First, it should have a strong expressive power. The language should naturally describe complex quantum state properties. The second one is efficient checking, is that, okay, the predict in the assertions can be checked within very few executions. And we believe that projections can be a sweet point for these 2 objectives. Before we go into the details, let's first review some basic properties of projection operators. A projection operators is a very common linear operators, and you can find its definition in every linear algebra textbook. In a Hilbert space, a projection will map a state onto a closed subspace of the original Hilbert space. And here we use the letter P to denote a projection. One important property of projection operators is that different projection operators corresponds to different unique subspaces in the Hilbert space. So we can actually use the letter P to denote the subspace of the projection P without ambiguity. When a state vector or mixed state row is inside the subspace P, applying a corresponding projection will not change the state, since they are already in the mapped onto subspace. Projections can naturally represent quantum predicates. A state is said to satisfy a projection P if it is inside the subspace. The idea of using projections as predicates first appears back in 1936, even before computer science appears. Also, projections can be checked up on projective measurements. And most physical quantum computers directly support projective measurements. For example, projection P, we can construct a two output projective measurement. The measurement operator for the true outcome is just the projection itself. And the other measurement operator is I minus P, and I is an identity operator here. This measurement output will be false. The measurement output will immediately tell us whether the test state row is in P or not. There will be some practical issues, but we will discuss them later. Now let's discuss the benefits of using projections. First, in terms of expressive power, projections are much better than classical languages. Projections can have different ranks to represent subspaces of different sizes. For example, in this line, we can see a projection with 0 onto 0, 0, and which means, okay, the correct state must be in the 0, 0 state. And the second one here, we have a rank 2 projection with 0, 0, and 1, 1, and the correct state can be the linear combination of 0, 0, and 1, 1. And on the other hand, we must notice that projections cannot accurately specify all possible states. For example, this state row with different values of alpha and beta are not distinguishable in the sense of projections. And the subspace will always be this subspace. This is because we are not doing a full tomography. But we argue that selecting projections as predicates will allow more efficient checking. So first, recall that, okay, when a state row satisfy P, applying projection operator will not change it. Therefore, when doing this construct the measurement based on P, we have the following three scenarios. In the first case, when row is in P, we will always have outcome true with probability 1 and the state is not changed in the measurement. When the state row is not in P, and it's possible that we can have outcome false. And then we know that, okay, the state is wrong, not what we expected, and we can stop and debug the program. It is still possible that, okay, even a row is not in P, we still have a property that we observe the outcome true. In this case, the state row prime after the measurement will satisfy P, because actually the projective measurement operator P here will map the state row back to the correct subspace. And it is actually doing a correction here. This feature allows runtime checking. We can, even some intermediate state is not correct. Once it's passed an assertion, it becomes it becomes correct. So the key question to checking efficiency is how many executions do we need? We believe that the number is small for projection-based assertions. From basic quantum mechanics, you can know that the probability of observing the true outcome is trace P row for projection P and state row. So suppose we repeat this assertion checking for k times. The probability of not observing any false outcome is trace p row to the power of k. When trace p row is not 1, this probability decays exponentially, and we expect to see a false outcome very quickly. But what if 1 minus trace p row is very small, which means, okay, trace p row is very close to 1, and so the the power of trace p row will decay very slowly. We argue that, okay, such error is not severe because the semantics of any quantum program are trace non-increasing quantum operations. And we have the following conclusion. For the same program S, if the two inputs are very close, for example, a correct state and a small error state with bounded by their trace distance is bounded by a small error parameter epsilon. The output will also be bounded by the same parameter. This means, okay, the two output states are also very close. After all these discussions, we can now define the projection-based assertions. It is basically a projection and a set of qubits denoted by q bar here. The semantics of the assertions is, okay, we construct a projective measurement based on P and then run this measurement to see if the outcome is true, we continue. If the outcome is false, we abort and report the termination location. And as we discussed above, this projection-based assertions allows multiple assertions per execution. So we can actually insert many assertions in a program. And in the paper, we study the statistical properties of checking a quantum program with multiple assertions, like how many executions are required to achieve a statically guaranteed program behavior. And we also have approximate projection-based assertions. All the details can be found in our paper. And before is the theoretical part, and now let's discussing some practical implementation issues. That is, the projective measurement constructed based on the projection P may not always be executable on a quantum computer. There are two constraints here. First is the limited measurement basis. Most quantum computers only support measurement along the computational basis, actually the day basis here. If, for example, in the first measurement is m true is 0 and m false is 1, and then, okay, this measurement can be directly implemented, just to measure the qubit. But if the measurement basis is not in the day basis, it's in the, for example, in the x basis, this projective measurement cannot be directly implemented. Another constraint, we call it dimension mismatch. Suppose we have an n-qubit system and the Hilbert space will be a 2 to the power n dimensional space. When you measure one qubit, the subspace is reduced by half and becomes a 2 to the power of n minus 1 dimensional space. And we can only measure an integer number of qubits in practice. So actually, we can only support projections with rank in 2 to the power of an integer. But we can have projections, for example, here in this example, we have rank P equals to 3, and such projections cannot be directly implemented. So we propose 3 transformation techniques to resolve all these constraints. And we first solve the measurement basis problem. We can add unitary transformations to adjust the measurement basis. We have a proposition here. If the projection with the rank equals to the power of an integer, then by matrix diagonalization, we can find a unitary and a new projection. And in this new projection, there will be all the measurements will be along the computational basis. And now the original assertion will be, okay, we first apply this unitary and then checking for this new projection and then apply the UP dagger to reverse the first UP. And here is an example. Suppose the projection P is an EPR entanglement state. The matrix form is here. And we can find UP and QP in the second equation. Notice, and this UP is actually a 1 CNOT gate and a 1 Hadamard gate. Note that, okay, the UP and QP are not unique here. In the null space of the projection P, the selection of UP can be very flexible. We now try to solve the dimension mismatch problem. We first consider one case that the rank is small. And the high-level idea is to combine multiple assertions to implement a projection with small dimension. We have the following proposition. For a projection P with rank P smaller than 2 to the power of n-1, we can find an array of projections that satisfies, okay, each of the P has rank 2 to the power of an integer, and then the original subspace is the intersection of the subspaces of in this array of projections. And then the original assert Q bar P will be transformed to an array of sub-assertions, and all these sub-assertions can be executed with the previous transformation technique. The only case left is when rank P is larger than 2 to the power of n-1. In this case, we cannot use intersections because the projections with rank P 2 to the power of n is the identity operator, which is trivial and do nothing. And however, we can opt that we will always have a reasonable rank, a meaningful rank P with smaller than 2 to the power n, and 2 to the power n is actually equal to 2 to the power of n plus 1 minus 1. And we already solved the case for rank P smaller than 2 to the power n minus 1. So if we can turn n to be n plus 1, we can solve this problem. So the solution is we introduce an auxiliary qubit A and initialize it to be 0. And now we have n plus 1 qubits, but we can still check for P. The new projection will be the projection of 0 on A tensors the original projection. The rank P is not changed, so it's still smaller than 2 to the power n. And now the assertion is transformed to assert A Q bar on 0 tensor P. So how to apply those techniques to briefly summarize, based on the different ranks of P in this assertion, we can apply all the 3 transformations according to the ranks, and then to make all the assertions theoretically executable on a quantum computer. In the last minute, I want to discuss about the automation issue. You may notice that we need to manipulate operators of size 2 to the power n when transforming the assertions. And also decomposing a large unitary into single qubit gates and 2 qubit gates is very hard. So it is possible to have simple assertion implementations that can be automatically managed by classical computers. We propose a technique called local projections. We can trade in some checking accuracy by only observing part of the entire system. The key idea will be, okay, by taking the partial trace on a large projection P, we can find a sound approximation of the original assertion. The local projection assertions will be applied on a smaller number of qubits, and the operators will be smaller. Finally, we propose, let me summarize this talk. We propose to check quantum program states with projections. And we find a new sweet point for experimental power and checking efficiency using projections. And we consider some practical constraints and propose several transformation techniques to make them executable. There were many more examples, like assertion examples, numerical simulations on real quantum programs, and formal descriptions and proofs of the propositions can be found in the paper. And here is the link. And that's it for my talk. So now let's take the questions.
Okay, thank you, Gushu. We are, the stream is a few seconds ahead of the Slack, so I'll just give it a moment to see if anyone wants to type some questions in there. In the meantime, I could ask, is there some relationship between this and error correcting codes, which have very much a similar idea that you're repeatedly doing projective measurements to see if you're in some subspace?
Yes. Actually, I believe, for example, in most quantum mechanical codes, you are using some redundancy by only force the correct state to be a subspace of a large of a large space. You are trying to force using projective measurement to force the error state back to the correct state. But in this example, we are trying to we are from the programming perspective. We are not dealing with errors from the noise from the computer itself. We are dealing with the if you write down something wrong. For this type of errors, you cannot detect it with error correction code because it's totally it's just at different layers.
Yeah, you're talking about logical errors in the program.
Yes, logical errors.
Ross Duncan asks, how about using this for error mitigation?
Yes. Actually, we have considered this, for example, in near-term noisy devices. If we can find some point, we can implement assertion with very few additional operations, and the implementation should be much simpler than the program itself, and then we may be able to correct some errors in reality, but we need to find such cases.
He further comments, I guess the hard part is working out what projection to choose.
Yes. In this paper, we assume that, okay, the programmers know about what he is writing. I can give an example here. For example, in chemistry simulation, the number of, for example, in the electron structure simulation, the number of particles must be reserved, which means, for example, in using some encoding, only a subspace of the entire space is valid, like a physically valid subspace. For example, you must have 2 electrons. You cannot, any state representing 3 electrons is not valid. So that's what, for example, the projection based assertions can be used here.
Okay, great. I think with that, I mean, you can't hear anyone clap, but I'll clap for you to thank you again,
Okay,
and all the
thank you.
speakers of the session. Before you all leave the stream, there were a few announcements that the organizers would like to make. So let's see. First, I should say tomorrow in the morning will be the morning UK time will be a quantum chemistry workshop, and IWQC will resume in the UK afternoon at 1 p.m. UK with Margaret Martinosi's invited talk. Ross also says if anyone fancies a beer right now, he's going to create some Zoom links for some virtual pubbing. And Katie says there will be a quantum companies in the UK panel at 8 p.m. Again, UK time this evening. So that's in 1 hour. So I think that's everything. Thanks again, Gushu.